All right, today we're doing 19.2 diffraction. So we'll talk about diffraction with single slits and diffraction gradient. You guys remember what Huygens principle is? I keep talking about it. You remember? You don't remember? Okay. Huygens principle is if you're standing out in the hall, it sounds like the door is making the noise. But if you poke your head inside the classroom, you can see that I'm actually standing on the right side in the classroom. So the door acts like a new source of the sound. So even though I'm in here and I'm talking and you get sound all over here, as soon as it hits the door, it seems like the door is the new source. We call this a point source. And each one of these waves is a wavelength. Now this works with sound, but it doesn't work with light. It works with sound in the door because the door is about the same size of the sound wave. It doesn't work with light because it's way too big. So what happens is the light casts a really big shadow over the light, so you don't see the wave nature of light because light is super, super duper small. But if we take light and we put it through a very tiny slit, one that's close to the same size of light, then you are going to get this wave nature of light. The smaller the slit, the more curves you get, the more diffraction you get, because that slit is super duper small and closer to the wave nature of light that will cut the light, and this diffraction pattern can be apparent. So anything that's a wave is going to have diffraction, just like anything that's a wave is going to have interference. We just don't always see it. So light does this with a very narrow slit. It's not going to do it with the door, because the door's too big. So a diffraction pattern is making these little curves visible. All right, this is a diffraction pattern. It is different than a double slit interference pattern. All right, double slit was from yesterday. We were talking about 2 point sources, 2 slits, and they interact with each other, and you get a striped pattern or a target pattern. Well, that pattern from yesterday, each of the bands were the same size. With a single slit diffraction like what we have here, you get a wide central band, and then as you move out, the bands get narrower and narrower. Now, if we use red light instead of blue light, and you compared them, like the same slit, the same distance, and you compared the two colors of light, your blue light's actually going to be narrower because it is a shorter wavelength. And if you did this with white light, you're going to see a mixed pattern of all the spectrums because blue light and green light and red light, they all have different wavelengths, so they're going to spread out and you'll get a rainbow. Now I could do a diffraction pattern up here for you with a laser. It's kind of hard to see, but I'm going to try to project it onto the ceiling with my mirror. Now all I have is a fancy laser, which you might be able to see the dot on the board right here. Kind of nice and boring. And then I'm going to put these two little razors in front. of the light, and I'm going to make a very narrow slit. They call this cutting the beam. Right? Cutting the beam. And the smaller I make the slit, the more apparent the diffraction beam is going, or the diffraction pattern is going to show up. It's crooked. Alright, so I'm going to try not to shoot the laser into your guys' eyes. And I'll project it onto the ceiling here. Oh, that's not a very good one. Let's try it. I don't think I know. Oh, that's much better. Okay. So, I'll move it all around so you can see it. But you see the bright central band and then the other bands on the either side of it? So I'll shoot it back there so you guys can see. Kind of like a UFO, huh? Right, so you guys are seeing a bright central band and then a couple of bands on either side of it. And if I change it, if I make it closer together, this band is going to get wider and these dots are going to get further apart. If I make it narrower, if I make it narrower, the band's going to get wider. If I make the slit wider, it's going to get all the way together until it turns into a dot. Now, I'll leave this up here, so if you want to look at it later, you're welcome to do that. That'll be after I'm finished. And I guess why I also have you guys here, I want you to put on your diffraction glasses. That is the fancy glasses. They're super awesome, and they make you look really cool. This is diffraction grading. I want you to take a look at the screen up here. What do you guys see? You see a rainbow? Okay. And then I want you to take a look at my laser light right here. You should look at the light that's a...
Oh my gosh.
Now this is a helium neon laser. And from chemistry, you should remember absorption spectrums and emission spectrums. This is an emission spectrum, and we will talk about this more later when we do light. But you're seeing the elements of the emission spectrum of helium and neon. There should be a couple of red lines and some other things. There's blue, green, and orange, I think. And we'll talk more about that in later chapters. And I'll try to steal the... there's a light that I can change out with different elements, but Spencer has it right now.
There's little things. She said there's red lines. He goes, yeah, and orange, yellow, and dark green. She's like,
Okay.
Ooh.
There we go. So let's calculate single slit diffraction. I'm just double checking, make sure that my... So here's some equations for your single slit diffraction equations. We have one for calculating the fringe and one for calculating the central band. For the fringe, this is how the location of the band of the fringe number, that's the little extra dots on the side, right? You have your central band, and then the next dot would be 1, and then the dot after that would be 2. That's the order band. So the distance that that band is from the center is x. The band number itself, if it's like the second dot away, then that's going to be n, so n will be a whole number. your wavelength lambda is going to be the wavelength of light. And in experiments, that's usually what you're trying to calculate. You're trying to find the wavelength of light. L will be the distance from the screen to the slits, just like yesterday. And W here is going to be the width of the slits. And that's kind of like yesterday, we're talking about the width between the slits. This one's the width of the slit. Now your next one is for just calculating that center band. We take M out since it's the central band, and we replace it with a 2 because the band goes on either side of the center. M is the order band. So on my little pattern here, I have like the central band, and then I have these little dots on either side of it. This would be the first order, the second order, the third order. So M is these numbers. And you can do it on the other side too. First, second, third. They should be mirrored images, so it doesn't matter which side you choose. And this will be your central band. Are we ready? Yeah. Okay. So diffraction versus interference. Diffraction, the wave is bending, and it makes the wave nature of light more noticeable. They use this as a much more accurate way of calculating wavelength. It's better than interference, they say. The slits, you have to be 10 to 100 times the wavelength of light. Now, the wavelength of light is between 400 and 700 nanometers, so that slit has to be pretty small. So my slit up here is probably 0.5 millimeter or something like that. Now larger openings, like a door, is going to cast huge shadows, so it's going to hide this pattern, the one that I've drawn up here on the board. It turns into just a dot because of all the overlapping shadows on it. So this would be diffraction. This is a diffraction pattern. And this one would be interference. This would just be like double slit interference. Interference. You would just have a stripe pattern. Okay. Now, diffraction grading. So this is single slit diffraction. You can have multiple slits on top of your slide or whatever you're putting through, and that is going to make the wave nature of light more apparent. Now, this is a Fresnel lens. It's a little bit different than a diffraction grading, but it's got a bunch of scratches on it. And these lines are, it doesn't tell me how close apart they are, but you can pass this around and see what happens to your vision. Now, it's not an actual like curved lens. This is called a Fresnel lens, and it just magnifies using a bunch of lines. So you can look at that and pass it around. It's kind of fun. Now, on your glasses that you have in front of you, your fancy glasses, that's a diffraction grating, and this spreads out the light. So what happens in a diffraction grating is that your laser light goes through, or some sort of light goes through, and it causes all of these, this pattern to line up on top of each other instead of being spread out. So you can still look at this without having a really tiny slit. And it is easier to take a lot of little slits with an average width than take one slit and try to get a very precise measurement of that. So this gives you very accurate information. So when you take your diffraction glasses and you look up at the light, you see that rainbow pattern. So the light is coming through, and it's that diffraction pattern is being all lined up so you can see the rainbow. Where when we just look at it, we see white light. But the diffraction grating spreads it all out so we can actually see the different colors of light. It separates them. Whereas this helium neon laser, there's only certain wavelengths coming off that light since it's pink, right? And these different emission spectrums line up to make that pink. And when we look at it with the diffraction, we can actually see the different lines. All right, we're ready? Now, diffraction gratings can have up to as many as 10,000 slits per centimeter. That's a lot. And the spacings of these slits can be as small as a micrometer all the way up to 1,000 nanometers. And they're just basically scratched lines. Now, holographic diffraction, it produces the brightest spectra. And they make them using lasers and mirrors, and this creates an interference pattern. Now, your 3D glasses, you know, those blue and red ones that you go to the movies and look through, those are either diffraction grating, which is less likely, or polarization, right? So what happens with your eyes, right, when we normally look at something is we see one image from one eye and one image from another eye, and they're just slightly offset, so we get a three-dimensional view. So they do that with your 3D glasses by making them polarized. So this one only lets in horizontal light, and this one only lets in vertical. So you put only vertical and only horizontal, and when you line up those pictures, you're seeing just a little bit different view of it. So your brain inputs those two images, and it makes it look three-dimensional, so it pops out of the screen. Where if you look at it without the 3D glasses on, it just kind of looks a little blurry, and that's because the images are just offset just a little bit, and you're seeing both horizontal and vertical with both eyes. So it looks blurry. I think this last little picture down here is the most interesting. You can see white light, and then again, remember that it's splitting up these beams, so you see all the blue light, the green light, and the red light separately. But when it's all on top of each other, you see the white light. I like that one the most. Okay, we're ready? All right, here's my last little set of equations for you. Should help you find this angle. The wavelength of diffraction grating can be found using the wavelength, the width, and the angle. Sometimes you might not be able to find that angle, so I've given you this little equation from trigonometry. And this is just the SOHCAHTOA stuff. Tangent equals opposite over adjacent. So if you're looking for this angle, your opposite is x, and your adjacent is L. So that'll give you your angle.
Yes, we did. They passed the test work and we passed it to them. Did you guys get this? Exactly.
Oh, you.
Right here.
And I think I just need to fix one little thing. One second.
I want to see I need it if you'd like to go and take it and make it.
I promise I'm going to
Yeah.
like floppy.
No, but
Okay, why? So you're going to do this?
yeah.
What would you say? Adjacent. Just say you're going to do pizza.
Because it's so like, because I don't like saying that sometimes.
Pizza.
Yeah, it's like me and my coworkers. It's getting into pre-kid age.
What?
He got my number from the public employee directory and then found my number. He used it to get my Snapchat. And so he's like my best friend because I keep opening the Snapchats without replying. That's how you get bugs from opening them. Yeah, bro. Yeah, he's something. And it's posted, it's in the employee directory. So that means like somebody needs to take a shift or something. We're like, oh, tomorrow's my grandma's funeral. Oh, let me call them.
Why grandma's funeral? Why did you pull that out of your head?
Because maybe they're grandma's.
Could I pull out like something that didn't?
Like, oh, tomorrow my sister's graduating.
There you go.
Okay, well,
A
funeral sounds much
February.
Not like grandma's funeral.
maybe a different state or country, I don't know.
My sister's graduating. Have fun.
All right, are we ready? No. Where is your cup?
Okay.
All right.
You need a cup for it?
I have like 5 clicker questions for you today. Here's the first one. So 410 nanometers of light shines through a slit and falls on a flat screen as shown in the figure, which is 0.29 meters away. The width of the slit is 3.8 times 10 to the negative 6. What is the width of the central bright band?